Okay guys, so here we go. This is it. The final video, the final lesson. So we've done the calculations now on parallel RLC circuits, and we've discovered this idea of power factor correction. Okay, so if I back up just a little bit and we eliminate this branch, here we go. We now have a circuit which is doing some work. We have a motor in our circuit, and we probably have a really terrible power factor, okay, 0.3 or 0.4 perhaps. And so in order to correct for that, we add to our circuit in parallel a capacitor. And this capacitor doesn't do anything, okay? It sits in the corner, collects dust, but we've connected it to our circuit for the purpose of power factor correction. We're hoping to get our power factor up to about 0.7, maybe 0.8, still lagging, okay, but a much better power factor. But this final lesson is about resonance. What happens if we overdo it? Okay, we add too much capacitance to our circuit, and we overshoot our power factor of 0.7 or 0.8, and we get all the way to a power factor of 1. We hit resonance, and what is the result? Well, I've drawn the parallel circuit here because let's go back to what we learned in a DC circuit, DC parallel circuit. What happens every time we add another branch? Okay, we actually reduce the amount of our total resistance, right? So every time we add a branch, we build another bridge across the river, we offer an additional path for current to flow, and we reduce our total resistance in our circuit. Okay, bring it back to an AC conversation, and we reduce the total impedance of our circuit. Okay, what happens when we hit resonance is these two currents cancel each other out, and it's like they're eliminated from the circuit. And now we're left, we break the circuit here, essentially there's no current flowing through there, no net current flowing through there, and the only current flowing through the circuit is through our resistive branch. Okay, so when we add additional branches, it reduces Z. As we remove those additional branches as options for current to flow, it increases Z. Okay, so here's the result. Let's erase this. And let's look at the chart and what happens to Z. And we're going to go back to the conversation about resonant frequency. So as we change frequency, the amounts of XL and XC adjust, and there reaches a point. Okay, what happens is as you increase frequency, you increase XL and you decrease XC until you reach a point where you have a resonant frequency, the frequency at which XL equals XC. So let's chart this based on frequency. Okay, what happens to Z as we approach resonant frequency? We eliminate those additional parallel branches, okay, which increases Z. And the result is this, and there's our resonant frequency, and Z peaks. Well, here's the question. Now, what does that mean for current? As frequency changes and we pass through resonant frequency, well, now the current does the exact opposite. And because of this peak in impedance, we actually choke out the current entirely. And so we have a really weird thing happen in a parallel circuit when we approach resonance, is we actually choke out the current entirely. And when there's no current flowing through the circuit, there's no work being done, because the equation power equals E times I is still true. And what happens when we run out of I? We're not doing any work. Okay, so in our industry where motors run everything, and we want to have these capacitors providing us with power factor correction, we have to be really careful that we don't allow ourselves to get our power factor too high. So that's why 0.7 is typically a target, 0.8 maybe, but we certainly don't want to exceed that. Seems like we might because feels like we save money. We're operating more efficiently. But in fact, the problem is that when we hit resonance, when we approach resonance, we choke out the current entirely and we don't get any work done. Okay, so it's a little bit of a hard thing to wrap your head around what happens in a parallel circuit when we hit resonance. But just like in a series circuit where we saw a spike in current, which was undesirable, okay, we get the exact opposite. We get this dip in current, okay, but that too is undesirable because the result is we just don't get any work done by our circuit. So things just get choked out entirely. Okay, so again, we're not going to do any math on this. That's just the concept. It's important that we understand that while power factor correction is a good thing, overdoing it is really problematic. Okay, so that pretty much is the end of what I had to tell you guys and teach you guys. Keep working on the exercise sheets. Work on the parallel RLC circuits specifically. Okay, that's kind of the end game here. This is everything we've done, all the math we've done, all the trigonometry was leading up to the parallel RLC circuits. That's the most realistic. That's exactly the kind of scenarios that we see in industry each and every day. Okay, that's the realistic circuit. And that's the kind of stuff, well, I mean, in terms of the test coming next week, it's going to cover everything, okay, all of the fundamental information building to that final circuit. So you can absolutely expect one of those on the test. Okay, everybody have a safe summer. See you in September.